Hi, everybody. This is example problems. Chapter 7. And we're starting with 7-7. 7-7 is motion with elastic potential energy. And it reads, a glider with mass 0.200 kgs. Sits on a frictionless horizontal air track connected to a spring with a force constant 5.00 newtons per meter. You pull the glider, stretching the spring delta x equals 0.100 meter, and release it from rest. The glider moves back towards its equilibrium position, x equals 0. What is its x velocity when x equals, so this is, sorry, that's x1, and x2 equals 0.080 meters, 0.80 meters. So we want to know its v when it gets there. So I'm going to calculate the difference in elastic potential energy and equate that to my difference in kinetic energy. So I know my kinetic energy, K initial, I'm holding is going to be equal to 0. And U initial is going to be equal to 1/2 kx squared is going to be equal to 1/2 times 5.00 newtons per meter times 0.100 meters. And that is going to be equal to 0.0250 joules, 0.250 joules. And my U2 equals 1/2 kx, this is 2 squared. That's going to equal to, did I square that? Sorry, that's supposed to be squared. 1/2 times 5.00 newtons per meter times 0.080 meters. And that's going to be equal to 0.0160 joules. So now I know K2 is going to equal to my U1 minus U2. That's going to be equal to 0.250 joules, 0.025 minus 0.0160 joules. And that value is going to be equals to 0.009 joules. All right. Now, 0.009 joules is going to equal to 1/2 mv squared. So v is going to equal to the square root of 0.009 joules times 2 divided by m, which is 0.200 kg. And v is going to equal to plus or minus 0.30 meters per second. Example problem 7a is motion with elastic potential energy and work done by other forces. And says, suppose the glider in 7-7 is initially at rest at x equals 0 with the spring unstretched. You then push the glider with a constant force F magnitude is going to be equal to 0.610 newtons, 0.610 newtons. In the positive x direction, what is the glider's velocity when it is moved x equals 0.10 newtons? So that would be delta x equals 0.100 meters. Sorry, 100 meters. So I'm looking for the glider's velocity at this point. Okay, so I start with a zero initial velocity, so K1 equals 0. My initial potential energy, U1, equals 0 as well. The spring is in its equilibrium position. K2 is going to equal to 1/2 mv squared. And U2 is going to be equal to 1/2 kx squared, which is equal to 1/2, and that was times 5.00 newtons per meter. And that's times 0.100 meters squared. And that's going to be equal to 0.0250 joules. I also have my work done by the force, work other, equals 0.610 newtons times that displacement, which is 0.100 meters, 100 meters. And that's going to be equal to 0.061 joules. All right, and my equation is K1 plus U1 plus work other equals K2 plus U2. So I've got 0 plus 0 plus 0.0610 joules equals K2 plus U2. K2 plus U2, and U2 is 0. Let's see, so U2. Where U2 would be 0.20250 joules. So I've got K2 is going to equal 0.0610 joules minus 0.0250 joules. K2 is going to be equal to 0.0360 joules, 0.0360 joules, and that equals 1/2 mv squared. So v is going to equal to the square root of 2 times 0.0360 joules divided by the mass, which was 0.200 kg, and that's going to be equal to 0.60 meters per second. 0.60 meters per second. Seven 7.9 is motion with gravitational, elastic, and frictional forces. And it reads, a 2,000 kilogram elevator. Oh, come on. All right, everybody, this is example 7.9. Example 7.9, you've got an elevator and its cables broke, so it's careening down. Well, hopefully not careening down. Anyway, it's coming down and it's got a frictional force and it's got an initial kinetic energy and it's got initial potential energy. And then it's going to come down to like this cushioning spring on the bottom. And we want to know what spring constant we need to stop this elevator. So let's go ahead and determine this. So we've got the elevator. It's got an initial kinetic energy when it encounters the spring 2 meters above the point at which it's going to compress the spring to. So we want to know the spring constant in order to get it to stop. So we've got K initial plus U initial plus work done by other forces, OF, equals K final plus U final. So this U is both going to be the elastic potential energy and the gravitational potential energy. So what do we got here? We got a mass of 2,000 kg. We've got initial velocity of 4 meters per second, pretty fast. And we've got the cushioning spring. We know that right when it touches a spring, that's the point we're interested, and it's going to compress it to a point of delta x equals 2 meters, 2.00 meters, 0.00 meters. Oh, yeah, and the frictional force is pretty deep. It's 17,000 newtons. So we want to know what the spring constant, what necessary spring constant we're going to need to stop it. So we've got initial 1/2 mv squared plus u, and your book does it a different way. I'm just going to go ahead and do it my way because your book is confusing me. So I'm going to say mgh plus work is force of friction times distance, and that's going to equal to 0 because we want to come to a dead stop, and plus the elastic potential energy. So it's going to compress that spring 2 meters, and that's going to give that spring elastic potential energy. So it's going to be equal to 1/2 kx squared. So we have 1/2 times 2,000 kg times 4 meters per second quantity squared, plus m is 2,000 kg plus 2 meters, because that's what 2 meters times g is 9.8 meters per second squared. These are both given in energy, these guys and that guy, right? And this guy's going to take some of the energy away, so that's going to minus 17,000 newtons times that 2 meters equals 0 kinetic, and its potential is going to be 0 plus 0 plus 1/2 kx. Oh, well, I'll go ahead. 1/2 times x is going to be that 2 meters quantity squared. So if you do all the algebra on this, you're going to come up with a spring constant of equal to 1.06 times 10 to the 4th newtons per meter. It's a bunch of algebra, but I'm going to leave that to your pleasure. Remember, it's getting energy at that point right about when it contacts the spring from this guy and this guy. That guy's going to take it away, and we're going to equate all that to this, right? So all this work is going to be done by is going to equal the work done by the spring, or the change in elastic potential energy by the spring. So that's 7.9. All right, 710 is going to be friction depends on path. So this is going to show us that friction is actually a non-conservative force. So it goes something like this. You're rearranging your furniture, and you want to move a 40-kilogram futon. Does anyone have futons anymore? Anyway, I do. A 40-kilogram futon. Yeah, mine's in my garage though. 2.5 meters across the room. So we want to, so the displacement, delta x, is 2.5 meters. And, but a heavy coffee table, which you don't want to move, blocks a straight line path. Instead, you slide the futon along a dogleg path. The dog legs are 2 meters and 1.5 meters. How much more work must you do to push the futon along the dogleg path than along the straight line path? The coefficient of kinetic friction is mu k equals 0.200. Mu k equals 0.200. Okay, so the force you're going to do, and I'm assuming you're not going to accelerate it, is going to be equal to the friction. You're going to push it along at a nice, steady, constant velocity. So it's on a flat surface in your home. Let's hope your home is flat. Mine is. I guess it would be cool if your home wasn't flat, but all the kids are doing the flat floors. Anyway, so we've got, we can either do a 2.5 meters, or we can do something like a 2 meters plus a 1.5. So either we take this guy, which we have to move your coffee table, and no one wants to do that, or here's your coffee table, it's right there, right? Or you just go around your coffee table. So the work is going to be done to the negative friction, which is normal force times mu k times the distance. So we either have 40 kg times 0.200 times a 2.50 meters. And let me erase some of this. I need a little clearness, a little board space. All right, and that versus, let's see, that versus the long way, which would be 40 kg times that same coefficient of friction, 0.200, times a 2.00 meters plus 1.50 meters. And so I'm just going to go ahead and use their examples. The first guy, you're going to do a 196 joules of work. And with that second guy, you're going to do 274 joules of work. So the amount more that you do is 274 joules minus 196 joules. And that's going to give you 78 joule more of work. So yeah, it's probably worth it so you don't have to move your coffee table. All right, everybody, this is example 711. And it is conservative or non-conservative? Okay. Okay, in this problem, you're giving a force. It's equals to Cxj, where C is a positive constant. And the electron moves around a square loop in the XY plane. So we've got this. And they're going this way, here, 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 and here. Okay, so this guy right here and this guy, your force is going to be perpendicular to your direction of motion. So the force is a function of the x component. So that's going to be 0. But here your force is going to be equal to CLJ. And here your force is going to be, it's CXJ, so x is 0 here. They call this 0.0000. So your force is going to be equal to 0 here. So the force goes this way. The force goes this way. The direction is perpendicular on those two. And here the force is 0. So the only leg that matters is going to be this. And your work here is going to be equal to the integral from y equals 0 to y equals L of CL dy. And so bringing CL out equals CL dy. And so evaluated from 0 to L, you're going to get CL squared. So it's not conservative. If it were conservative, you would have a zero force because you have zero displacement. So it is a non-conservative force, that one. Conceptual example 712 is work done by friction. Work done by friction. Okay, and it states, let's return to example 7.5, in which Thraki skateboards down a curved ramp. He starts with 0 kinetic energy and 735 joules of potential energy. And at the bottom, he has 450 joules of kinetic energy and 0 potential energy. Hence, delta K equals plus 450 joules and minus 735 joules. The work other done by the frictional force is negative 285 joules. So the change in internal energy is plus 2 is the U internal equals negative work, and that's going to be we already know the negative work, the work is negative 285, so it's going to be 285 joules because the friction does